This is video 11.3, and today we're going to be talking about limits and continuity. The first objective in this section is going to be to determine if a function is continuous at a given number. Now, the first thing we want to do is make sure we know the definition of continuous. Continuous means there wouldn't be any breaks in the graph. So if it's continuous, there are no breaks in the graph. One way you can think about it is, can you draw without picking up your pen? Now, you can see on all three of the pictures below, any of those I want to draw, I'm going to have to go ahead and pick up my pen in order to finish the drawing. I can't draw them without picking up my pen. On this first one here, when I get to the x value of a, all of a sudden there's a hole. I'd have to jump over it and pick up my pen. Same thing on this one. There's a hole, so I would have to at some point pick up my pen, and you can see it jumps from one number to one y value to the next. And even on this other one, I have to pick up the pen to draw it. So none of those would be continuous. All of them would be discontinuous. They wouldn't have continuity. Now, to determine if a function is continuous given the equation, we have to check a few different things. The first thing we're going to want to check is, does f of a equal a number? Now you can see in this first picture here that f of a is an open circle. In this case, f of a is no solution. There is no number. There is no y value when x equals a. That would then tell me right away that this function is discontinuous. Now, if it passes that, then we go on and check the next thing. The next thing we need to check is, does the limit as x approaches that number exist? Now, you can see, for example, in part B, that as I'm approaching a up here, the limit goes from both directions to a different number. So in this case, the limit as x approaches a does not exist. I'm just going to put D and E. Now, because the limit does not exist, that means that there has to be a jump somewhere in the graph. So if it doesn't pass number 2, that means that the equation is not continuous. Now, if it passes number 1 and it passes number 2, you have to check one more thing. You need to make sure that the answer from number 1 equals the answer from number 2. So f of a has to equal the limit as x approaches a. If you look at the third graph, the limit as x approaches a, let's say that limit was 5. But f of a maybe equals 6. So that tells me, because those aren't equal, that that graph is not continuous. Now, if you pass all three of these, to be continuous, then it's continuous. So if you pass all three of those options, then the function is continuous. So let's go ahead and take a look at an example. We have f of x equals 2x plus 1 over 2x squared minus x minus 1. And we want to know if it's continuous at 2. So a equals 2. And we're just going to go through and check all of those things that we wanted to check. The first thing we want to check is, does f of a exist? So we need to find f of 2. We'll go ahead and plug a 2 in for all the x's and see what we get. On top, we get 4 plus 1, which is 5. On the bottom, let's see, we're going to have 4 times 2, that's going to be 8. Minus 2 minus 1, that's another 5. And 5 over 5 is 1. Since f of a exists, we go on and we check the next thing. The next thing we need to check is the limit as x approaches 2 of f of x. Now, the next thing is using the properties we learned for finding the limits, we can go ahead and just plug a 2 in for all the x's. Remember, it's the limit of a quotient, so we can find the limit of the top and the limit of the bottom. And if I plug a 2 in for all the x's, I get the same answer as I had above. Remember, what we're doing is we're finding the limit as x approaches 2 of 2x plus 1. And the limit as x approaches 2 of 2x squared minus x minus 1. That's the quotient rule we learned yesterday. Now on the top, you can see if I plug a 2 in, we'll get a 5. And on the bottom, if I plug a 2 in, I get a 5. So it passes number 2. The limit does exist. Finally, option 3, we want to know if both of those are equal, and they are. So yes, it is continuous at 2. Let's go ahead and look at another example. We're going to use the same function, only now we're going to change the a value. Now we want to know at 1. Is this graph continuous at 1? So, to decide if it's continuous at 1, we go through all the same steps as earlier. So the first thing we're going to find is f of 1, and we want to know, does f of 1 exist? So we'll get 2 times 1 plus 1, 2 times 1 squared minus 1 minus 1. On the top, we get 3, and on the bottom, it looks like we're going to get a 0. And so in this case, we get no solution. So that means that no, this function is not continuous at 1. We can stop there. Now, I'm going to give you one to try. So go ahead and pause your video, and I want you to determine if this function is continuous at 1 and also at 2. So go ahead and check it for both of those. All right, you can go ahead and check your answers and see how you did. And this is where we'll end the video for today.